Okay, so unfortunately, when I did the problem and I tried to record myself, it got deleted. So I basically wrote down the notes. So you're just gonna have to see the notes pre-written. Okay, usually I would write it as I explain it. Okay, so over here on number 7, right, it says you're training to run a marathon, but you've never ran one before, and presently you can only run 2 miles before passing out. After 4 weeks of training, you can now run 3.5 miles, assuming your progress continues exponentially. How many miles can you run in 16 weeks? Okay, so the equation I'm going to use is y is equal ab to the x, or ab to the t. And the question is, how do you know when to use that? So whenever you're just given a general pattern, right? This is one of those pattern problems. Okay, in week 1 you have this amount, week 2 you have this amount, right? And so if you're just given a specific pattern and it says it's growing exponentially or decaying exponentially, you could just use the generic formula, right? So I'll go over this equation in class when we graph exponential functions. Okay, so over here I kind of made a table, right? In week 0, that you can run 2 miles. Week 4, you can make 3.5 miles, right? And week 16, how many miles can you run? So basically I plugged it in twice, right? For t is equal to 0, y is equal to 2. If you solve this, right, b to the 0 is 1, you're going to get a is equal to 2. And for t is equal to 4, right, y is equal to 3.5. So since you already solved for a, right, you can just plug it in over here and get b by itself. So when you get b to the 4th is equal to 1.75, to get b by itself, you take the 4th root, and you could just say, hey, b is the 4th root of 1.75. Okay, so once you have a, once you have b, this is your equation, and then you can plug in 16 to get 18.8 miles. So that's all there is to number 7. All right, so for number 8, the nice thing is they already give you an equation. It says when a plant or animal dies, it stops acquiring carbon-14 from the atmosphere. Carbon-14 decays over time with a half-life of 5,730 years. So if you're wondering what half-life is, it's just the amount of time it takes for a substance to reach half its amount. Okay, so the number 5,730 is the number of years it takes carbon-14 in a particular animal or organism to reach half its amount. All right, so P is the percentage and T is the time in years. So on part A, it asks you to determine the initial percentage. The initial percentage is basically when T is equal to 0, okay? And you could just identify that, hey, this is my initial value, right? This is 100. Or if you could just plug in T equals 0, you will get 100, okay? Anything raised to the 0 power is just 1. 100 raised to times 1 is just 100. For part B, it's a straightforward plug-in, right? Plug it in when it's 2,500 years, 5,000 years, 10,000 years. That's the percentage that you'll get if you enter it on your calculator. Part C is just a graph. Okay, so I added some additional points, P of 18,000, P of 9,000. And roughly, this is what your graph looks like. Okay, so in class on Monday, I'm going to teach you guys how to graph, depending on which period you're in. Period 4, you'll meet me in class on Tuesday. I'll teach you how to graph the exponential functions. Okay, so over here, there's a horizontal asymptote, right, at the x-axis. Okay, so plug some points, connect it as a curve. And then part D asks you estimate from the graph the age of the bone if the bison bone is 37%. So 37%, I would say, roughly around here. And then it hits the graph right around there. And, this is an estimate, right? So I would say between 8 to 9,000 years as my estimate. Later on, right, what you do is you take P of T is 37 into this equation and you plug it in, right? And then you solve for T. Later on, we're going to do that exactly, solving an exponential equation instead of roughly estimating. And the way you do that to solve for T, right, is just to use logs. Okay, so last but not least, the domain, reasonable domain in this problem, right, is from 0 to infinity. And the range, right, because this graph has a horizontal asymptote at the x-axis, it's never going to hit the x-axis, but it's going to go from 0 to 100. And the question is, will the percentage of carbon-14 ever reach 0? And the answer is no. It's not mathematically possible. Why? I showed you over here, P of T is equal to 0, T is equal to what, right? So if I just set P of T is equal to 0, there's no number for T that's going to exponentiate this 1/2 right here such that I get an output P of t is equal to 0, right? Or even simpler, forget that equation. Can you think of a number that I raise 1/2 to a power of such that I get 0? Usually we would try positive numbers. There is no positive numbers. Well, what about negative numbers? Negative numbers is not going to give you an output of 0 over here. Well, what about 0? Well, anything raised to the 0 power is just 1, right? So the answer to that is that it's not mathematically possible for this graph to ever hit the x-axis. It'll come close, but it will never ever actually cross